All right, let's do a few more examples where we figure out empirical formulas. And I also want to go in the opposite direction. So in this example, we're going to use masses to figure out empirical formulas in a similar way that we used mass percent composition to figure out empirical formulas in the previous lecture. And then in the next example, I want to go in the opposite direction. Given an empirical formula, can you figure out the mass percent compositions? So I want you to be able to do these problems backwards and forwards. All right, this problem puts a little bit of a twist on the concept because I am making you think about a chemical reaction. Let's say that 10.00 grams of phosphorus reacts with oxygen to produce 17.77 grams of a phosphorus oxide compound. What is its empirical formula? Can we use this information to determine the empirical formula of the compound? So here you have to think about what's going on. You're making a phosphorus oxide compound that contains only P and O. And you know how much P you have, and you know how much of the total you have. Can we figure how much oxygen we have? We need to determine how much oxygen because we need to figure out the molar ratio of phosphorus to oxygen or oxygen to phosphorus, because that literally is what the empirical formula is. It's the whole number ratio of those two elements to each other. So here, if I have 17.77 grams total, and 10 of those grams were phosphorus, that should give me the number of grams of oxygen, because I need to obey the law of conservation of mass, right? Matter can neither be created nor destroyed. So if I'm making 17.77 grams, then 7.77 of those grams must come from the oxygen. So now at least I have the masses of each element. So I can take those masses and turn them into moles using the atomic masses from the periodic table. So I have 10 grams of phosphorus and 7.77 grams of oxygen. The periodic table gives me the atomic mass of phosphorus as 30.97 grams per mole. So if I do that, I can cancel out the grams and I can figure out the number of moles of phosphorus that mass represents. So I didn't need to assume 100 grams or anything like that in this problem because I actually know the absolute masses. So I can figure out the number of moles in that absolute mass. 7.77 grams of oxygen, I'm going to multiply that by the reciprocal of its atomic mass, which is 16. And that is going to give me 0.486 moles of oxygen in that mass. So I'm going to divide through by the smallest number. So my oxygen, there's more oxygen than there is phosphorus. So the O to the P ratio is going to be 0.486 to 0.323. So that is equal to 1.5 or 1.5 to 1, right? So I need to 1.5 to 1. I need to multiply through by a common factor. And the common factor here is going to be 2 because I have a half. So I need to transform this into a whole number ratio by multiplying by 2. So 1.5 to 1 is equivalent to 3 to 2. And that is going to give me a formula of P2O3. So literally, this ratio becomes the subscripts in the chemical formula. So this is the empirical formula of my phosphorus oxide compound, the lowest whole number ratio of phosphorus and oxygen in that compound. So now I would like to start with mass percent I would like to start with a formula and determine the mass percent composition of the elements in that compound. So here is another example. What is the mass percent composition of iron and oxygen in Fe2O3? So I'm given the formula. Can I figure out the mass percent composition? So once again, the formula here, this is a molecular formula, but it's also the lowest whole number ratio. So the iron to oxygen ratio is equal to 2 to 3. And that is the best way to solve a problem like this is to assume you have 1 mole of that compound. Assuming you have 1 mole of the compound, you are going to have 2 moles of iron and 3 moles of oxygen per mole of that compound. So now we can go to the periodic table and get the atomic masses. The atomic mass of iron is 55.85 grams per mole. And here I'm not taking the reciprocal, right? I want to cancel out the moles and be left with grams. So I am just going to multiply the number of moles by the molar mass of each element here. So doing that, I cancel out my moles and I get 101.7 grams of iron and 48 grams of oxygen. So that is going to give me the number of grams of each atom in the compound. And I can also figure out the molecular or molar mass of the compound, of the whole thing, of Fe2O3. And I can do that just by adding those two numbers together or by just looking in the periodic table. It doesn't really matter. It looks like it's going to be 159.70 grams per mole. Okay, I just get that by adding 111.7 plus 48. Now it's very simple to figure out the mass percent of each element. The mass percent of iron is going to be 111.7 grams divided by the total, 159.7 grams. And that is going to give me a value of about 70 or 69.9%. The mass percent of oxygen should be 100 minus that. But just to make sure, I'm going to take the 48 grams and divide it by the total, 159.7 grams. And that gives me the remainder, which is 30.1%. So this would be the mass percent composition of both iron and oxygen in Fe2O3.